Okay, so in this video, we are going to talk about exponential functions and kind of more specifically exponential growth and decay. So today we're going to identify the exponential growth and decay graphs, just what they would look like, and then some equations we're going to match to exponential growth and decay. And we also want to create our own exponential growth and decay equations given a certain word problem. So the first thing I want to do, just as a little example of where these may come from, is a folding experiment. So you're going to need to go find a piece of rectangular paper. Regular size paper would be great, but really any rectangle would be fine. So if you need to pause the video for a minute and find some rectangular paper, go do that. So hopefully you are back with rectangular paper. And what we're going to do is we're going to fold that in half. Okay, you could do it hot dog or hamburger, it doesn't matter. But that's going to be one fold. And now when you unfold that, you should see two sections, right? Two rectangles. Okay, so that's what we're going to put here. And then we're going to fold that back the way it was, and then again one more time. So you're folding that in quarters. Okay, so that's only two folds. But if you were to open it back up again, you'll see four sections, and that's what this picture is over here. You see the 1, 2, 3, 4 sections. So we're going to keep doing that until we can't fold the paper anymore. Okay, so let's fold that back up the way it was, and then one more time. That's 3 folds. And if you open that up again and you count all of those sections, you should have 8 total sections. Okay, so we're going to keep doing that. We're going to keep folding and unfolding and counting sections. So fold that back up and fold it one more time. And then unfold it and count all of the sections that you see. You should get about 16 sections, not about, you should get exactly 16 sections. And then let's see if we can fold it one more time. This might be getting to be pretty difficult to fold, but let's see if you can fold it back up and one more time. And then unfold and count those sections. Perhaps by looking at the pattern in the number of sections, you might not even have to count them. You might notice that that should end up being 32 sections. Now, we can try to fold it up one more time and see if we can fold one more time, but my paper is getting kind of difficult to fold. I don't know about yours, so I might stop at the 5. I think I could probably get one more fold in there if I tried really, really hard, but I think maybe that's good enough for now. Okay. So the patterns that we notice in the table, I want you to look at these sections. It looks like each time we have doubled the number of sections that we have. Okay, so that's what we're going to be looking at when we look at what's called exponential growth. We're going to be looking at some sort of pattern that gets doubled or tripled or multiplied by some number bigger than 1 for exponential growth. So what I did is I took these coordinate points and I put them into a table on Desmos. Okay, so here's our table. Here's our graph. So I put these into a table on Desmos, and then I put a little graph through them. So here is our exponential growth graph. Some key things to notice that we'll talk more in detail later. The domain is all real numbers. It's negative infinity to infinity. This graph goes forever to the left, and then it will keep slowly going right forever, shooting up quickly, but slowly going to the right. The y values show that pattern of multiplication. We go from 2 to 4 to 8 to 16 to 32. So our exponential growth equations will show that pattern of multiplication by some number that's bigger than 1. On the left side, this graph really flattens out. Now it's hard to tell here. It flattens, but it never quite gets to the x-axis. It gets really, really close to the x-axis, but never quite gets there. So we say that it approaches y equals 0, and that's something that we'll talk more in depth about at a later time. We can also take a look at what's called an exponential decay function. So this is almost like a mirror image of what you just saw. So it has some similar characteristics. The domain is still negative infinity to infinity. This still will go slowly left forever and to the right forever. The y values still show a pattern of multiplication, but it's by a multiplication of a number less than 1. So we go from 16 to 8. That means we've multiplied by a half. And then we go to 4, 2, and 1. We keep multiplying by 1/2. So you'll notice with our exponential decay functions, we still see a pattern of multiplication, but that multiplication is by a number less than 1. In this case, it was by a half. One side of the graph still approaches 0. It's just the other side of the graph. So over here, we still have this graph that's trying really hard to get close to the x-axis, but it doesn't actually ever get there. And that's, again, something we'll kind of talk more in depth later. Okay, so here are there two exponential equations, one for growth and one for decay. So you'll notice that they're very similar, except for a plus sign for growth and a minus sign for decay. Other than that, both functions are identical. The a value represents our initial amount. In order for something to grow or decay exponentially, it has to start somewhere. So the a value represents that initial amount. This r value here is the rate at which it's growing. So if we are growing by maybe 50% each time, this rate would represent that 50%. The same exact equation except for a minus sign. So again, this is our decay rate, this r, but you'll notice we're taking it away. So this is trying to show the fact that we are going to end up with multiplying by a number less than 1, and that will show a decay. Those numbers will go down. So let's do an example of exponential growth. So if we take a look at this question, this is talking about the population of a Framingham, which grows at a rate of 2% every year. We want to know what the estimated population will be in 5 years. Okay, and down here, we are told what our population is right now. So this is exponential growth. I say exponential growth, but I'm also really emphasizing that in the equation by talking about growth. So we are going to write down our exponential growth formula, a times 1 plus r to the x. Okay, so we need to fill in our initial amount and our growth rate. The initial amount is our 72,000. That's what our population is now. That's where it's starting. Now, our growth rate is 2%. We do not want to leave that in percent form. We're actually going to change that to a decimal. So 2% means 2 out of 100, which means a decimal of 0.02. So we don't want to use the percent in our equation. We are going to use the decimal in our equation. So 0.02 instead of just 2. And that is raised to the power of x. So in this example, x represents the years and y represents the population. So we would like to know what the population of Framingham will be in 5 years. So we know that we want x to be 5. So we would like this number to be 5. And let's find out what that means for y. So y equals 72,000 times 1. Let's see. 1 plus 0.02. I'm actually going to add that together and just call that 1.02. And we will raise that to the 5th power. Okay, so I'm using 5 in for x because x is our years. And I'm using 1.02 just because I combined 1 plus 0.02. So this is something that we are going to need a calculator for. So we'd want to go find either a calculator on our phone or on the computer. I'm going to use Desmos. So this is a Desmos scientific calculator. So I can type in 72,000 times 1.02 raised to the 5th power. And the answer is over here. So the answer is 79,493.8. I'm just going to round that to the nearest whole number because we're talking about people. So we want to make sure to round that to a whole number. So I'm going to call this 79,494. We will say 79,494 people. In 5 years. Okay, so let's do an example about exponential decay. A video is labeled a fan favorite if it receives at least 1,000 views per day. Amelia posts a video that gets 8,192 views on the first day. So we're kind of calling that time 0. The number of views decreases by 25% each day after that. In how many days total will the video stop being a fan favorite? So, this was obviously written out as an exponential decay equation, but we also have this keyword in here of decreases to remind us that this is actually a decay. So I'm going to write down our decay formula, and let's fill in both the initial amount and then also the decay rate. So for an initial amount, that was the initial number of views. So that was 8,192. The decay rate comes from this 25%, but we're not going to write it as a percent. We're going to change that to a decimal by dividing by 100. So our decay rate is 0.25. In this equation, our x represents the number of days, and our y represents the views. So this question is looking for when our views get down to 1,000. So we are looking for when y is equal to 1,000. So I'm going to use 1,000 in for y. And then I'm also just going to simplify the inside here. 1 minus 0.25 comes out to 0.75. Okay, so we'll notice that that value is below 1, right? This is less than 1. So that's another reason why we know that this will be a decay. So this is going to be a little bit more difficult to solve than the previous question because I need to solve for x. This is not just typing this into a calculator. I've got a left side and a right side to this equation, and I need to solve this. So I'm still going to use Desmos, but I'm going to use the graphing portion of Desmos. My plan is to type this into one of the lines on Desmos and this into the next line. And we'll find when they are equal, when they meet. Okay, so I've typed in 1,000 in one of those lines. I did y equals 1,000, and then my equation into the other line. Now I need to see where these meet. So if you are on kind of the original screen, this doesn't show anything. So, these numbers are so large, 1,000, I'm only going up to 6 here. So I think we're going to need to zoom out. So hopefully you'll see the exponential decay. And then once we get to 1,000, you'll see that straight line across. So I am looking for when these meet. So I'm just going to click there to see where they meet. And you can zoom in if you need to, if that's easier. So the point where they meet is 7.311, 1,000. So I'm going to go back to my slides, 7.311. So the point in which they met was 7.311, 1,000. So we knew the y value was going to be 1,000. That's what we were looking for. It's the x value that will solve for us. So x is 7.311, and our x value was days. So in about 7 days, maybe a little more than 7 days, the video will get down to 1,000 views per day. Okay, so the last thing that we want to be able to do is identify from an equation whether we have growth or decay. And so this is going to be based solely on what the base of our exponential equation is. So I'm going to be looking for the number that's being raised to the power. When that number, which we called the 1 minus r value, sometimes we call that the b value, when that number is less than 1, we are going to have a decay. So because 0.5 is less than 1, this means we have a decay graph. When that number is bigger than 1, we will have a growth. So this one's a little bit easier to see that it's growth because I can see that plus sign that's a part of my growth formula. But 1 plus 0.3 is definitely bigger than 1. Right? 1 plus 0.3 is 1.3. So this must be a growth. So we are looking for if our number that's being raised to the exponent is bigger than or less than 1. So this number right here, 1 minus 0.2, that's 0.8. So this has to be a decay. We can also see the subtraction that shows up in our decay formula. This number right here is less than 1, so this must be a decay. And this number is larger than 1, so this must be a growth. So notice the initial amount, okay, the initial amount, which in this case is a 1, this one's a 2, 100, 0.5, and this is a 1. The initial amount does not matter at all. All that matters for growth and decay is what number you're raising to the exponent. If that is bigger than 1, that is growth. If that's less than 1, that will be decay. We'll take a look at this in more depth in the upcoming days.